we now come to temperature. And as this video is being recorded, July of 2024, the United States is experiencing a fairly strong heat wave across a lot of the country. And where I am, where this video is being recorded, we've been in triple digits the whole week and will continue to be for essentially the foreseeable future, the next several days. So, this whole idea of temperature, right? We have an innate sense of it, um, just because we have to refer to different weather stations, the weather channel, weather apps, and things like that to understand how to dress for the day and for the season. If you're sending your children to school, then you dress them appropriate for the season and for that day's temperature. If it's going to be really, really hot, you generally don't wear really thick hoodies the same way that you would in the winter. So, what is this thing called temperature that governs a lot of our behavior? So, your textbook has a delightful little sentence, and paraphrased, uh, it says one way to define temperature is the thing we measure with a thermometer. And that's all well and good. Not very enlightening, right? So, first of all, we have to, ask what is a thermometer. And we would say what we use to measure temperature. And at first you might be like, wait a minute, this is circular reasoning. And if this was the end of the story, you would be right. This would be circular reasoning if we didn't have any more clear cut way to define things. We will see, we are not going to go through the argument here, but we will later. But we will see that we can actually put temperature on a more firm physical footing. And temperature, we can say, is a quantity of a system that is proportional um, and we will define what this means. Okay, average kinetic energy of translation. Um, but operationally, what this means is when we say it's 90 degrees outside or 60 degrees outside, we're talking about the temperature in the atmosphere. And so this average kinetic energy would be the average kinetic energy of the molecules in the atmosphere. Okay. And translation means the motion of the atoms in a linear fashion. Now, the atoms can be bouncing around off of each other and things like that, but we're talking about their straight line kinetic energy in between collisions. we're not talking about how the molecules can twist. We're not talking about how the molecules can stretch. We're not talking about how the molecules can spin, that kind of kinetic energy. We're just talking about the kind of kinetic energy that we would typically associate with things like a pinball as it's bouncing around inside a pinball machine. Okay, so that's what we mean by translation here. So if we can find an estimate for the average kinetic energy, then that allows us to say something physical about the temperature, and therefore that fixes what the thermometer is measuring. So when you put a thermometer in thermal contact with some substance, you are measuring a quantity that is proportional to the average kinetic energy of the molecules in that system. Okay? So, thermal equilibrium requires two substances, two or more, could be or more, but a minimum of two substances. Okay. And we place them in contact with each other. Okay. So when two substances are placed in what we call thermal contact means that energy can be transferred between the objects. Okay. Now let's kind of look at this kind of on a blown up microscopic scale. Let's suppose that these are two blocks of the same type of material. Okay. It doesn't matter what they are. It could be wood, it could be steel, it could be whatever you like. All right. But imagine these are two cubes of the same material, and they are placed in contact with each other, and we can then say that they are in thermal contact. Now, you don't have to be in physical contact to be in thermal contact. And you know this if you've ever sat around a campfire and you felt the heat coming off of the campfire, you're in thermal contact with the heat, with the fire. That fire is able to transfer energy to you even though you're not touching the fire, or at least hopefully you're not touching the fire. And so let's suppose that the temperature in block A is larger than the temperature in block B. So what this means is that if I look at a few atoms in this substance, if temperature is a quantity that is proportional to the average kinetic energy of these molecules are going to be randomly jittering around. Now, let's say that, let's actually get rid of the solids, okay? So don't think of steel, don't think of, wood. Think of two gases that are brought into contact, okay? And so this is the velocity. These are the velocity vectors. So even though the velocity vectors, kind of crossing the boundary, that doesn't mean that the physical path of the atom is crossing the boundary. It just means that this is the magnitude of its velocity. So therefore, this velocity vector will be how we measure the kinetic energy then from 1/2 mv squared. So the molecules in this substance, their average kinetic energy is proportional to the temperature, right? But if a substance B, if gas B has a smaller temperature, a lower temperature, then the kinetic energies of these gas particles is not going to be as much. So the velocities are going to be less. So what that means is if we then remove any sort of boundary between these two and we let the two gases mix. When these atoms collide, if this atom, say, were to collide, so this atom moves this way, and it collides with this atom, at this point right here, the atom from block A, or substance A, has a much higher kinetic energy and therefore momentum, and therefore as a result of this collision, it will impart more of its momentum to the smaller particle. And as a result, the kinetic energy of the smaller particle increases at the expense of the kinetic energy from the particle in substance A. So after a while, what happens is, because of these collisions, eventually all of the, if they're allowed to interact and exchange energy, all of the atoms will eventually reach the same average kinetic energy. In substance A, the kinetic energies will be less than they were before. They'll still be randomly oriented. These molecules are just bouncing around in here. But the molecules in substance B will also have the same average kinetic energies, and they will be larger than they were before. And at the point where the kinetic energies are effectively the same, there really is no net heat transfer. Or I really should say energy transfer, because we haven't defined heat yet. But no net energy transfer. So there's a deep implication here, and that is, if two things are brought into thermal contact and they don't have the same temperature, you will always observe the hotter thing get cooler, but the cooler thing also get hotter to reach equilibrium. You will not see, as a result of these collisions, you will not see particle, if this is a particle from substance A with a, kinetic energy or a velocity vector like this, and particle B, a particle from substance B, and they collide, you will not see particle A increase its velocity at the expense of particle B. Okay? So this does not happen. You always will see, on average, particle A after the collision and particle B after the collision reaching toward a common value. Okay? So what that means is that heat will always be, energy will always be transferred from the hotter substance to the colder substance. Okay? So this brings us to what we call the Zeroth Law of thermodynamics. So, by the way, no net energy transfer, this is what we call thermal equilibrium. Now, the Zeroth Law of thermodynamics is one of the reasons why thermometers work. But the Zeroth Law basically says, if I have substance A and I have substance B, and I put a thermometer in substance A with the appropriate tick marks, right? If, well, let me put it over here. What the zeroth law of thermodynamics says is if our thermometer so in other words, there's no heat transfer between the thermometer and substance A. Okay. Now, energy can travel across the boundary from A to B, or not A to B, but from the thermometer to A or from A to the thermometer, but there's no net, right? So any energy that's transferred over the boundary has an equivalent amount also going the opposite direction, right? It's like free trade. You can just go wherever you like. So if the thermometer is in thermal equilibrium with A, meaning no energy transfer across this boundary, and A is in thermal equilibrium with B, then the thermometer is in thermal equilibrium with B. So in other words, if I pulled the thermometer out of A and stuck it immediately in B, then there wouldn't be any energy transfer between the thermometer and B either. Now, why thermometers work? So historically, when you had an alcohol thermometer, right, you would have your glass casing and maybe some sort of metallic holder down here, and then your thermometer would be filled with alcohol. It would have a thin line of alcohol. Often it would be red, right? So your reservoir would be down here. Your alcohol reservoir would be down here. And then you would have a thin tube where your alcohol would rise or decline, rise or lower, based on the thermal properties between the metallic holding and the reservoir here. So you would have your substance, you would embed your thermometer in your whatever it was. Let's say you're measuring the temperature of some water. So the water would have a certain temperature. The metallic shell would have a certain temperature. Your metallic shell. But then the alcohol would also have a temperature. And so because the metallic shell and the alcohol are constantly in contact, they're going to want to be in thermal equilibrium. And when the temperature of the metallic shell changes, that sends the signal to the alcohol that it needs to adjust its internal energy to match that of the metallic shell. So when you input your thermometer into the water comes into thermal equilibrium with the metallic shell. And then once the alcohol has reached whatever level it's going to rise or fall at, then your metallic shell is in equilibrium with your alcohol. And therefore, by the zeroth law of thermodynamics, you can claim that the water is in thermal equilibrium with the alcohol. And therefore, the ticks on the thermometer give you an accurate reading. Okay? Now, the zeroth law of thermodynamics does not explicitly state thermometer. Okay? It will typically use substances A, B, and C. So a more precise way to state the zeroth law of thermodynamics is if substance A is in thermal equilibrium with substance B, and substance B is in thermal equilibrium with substance C, then substance A is in thermal equilibrium with substance C. Okay, so that's like just being generic. Um, okay, so but the zeroth law just says if A equals B and B equals C, then A equals C. Okay, there's nothing mysterious or strange here, but it is somewhat a deep concept in that you have to recognize that there's no net heat transfer across these boundaries once things are in thermal equilibrium. And it might seem like a redundant or a uh, superfluous step to state, but it actually really is necessary. Okay. So what about temperature scales? How do we measure temperature scales? Now, we're not going to go into all of the history behind the Fahrenheit, Celsius, and Kelvin scales. We'll just hand them to you here. But the textbook has a chart that allows you to calculate your temperature for a given substance in one scale and how to convert it to another scale. And it gives you all six variations: Fahrenheit to Celsius, Fahrenheit to Kelvin, Celsius to Fahrenheit, Celsius to Kelvin, Kelvin to Fahrenheit, and Kelvin to Celsius. You really only need two, and then you can reverse engineer everything else. So I'm only going to give you two. Okay. But first things first, how do we spell these things? So the three, now these are not the only temperature scales that are in use, okay? But these are the three most common, particularly here in the United States. The Fahrenheit scale, Celsius, and Kelvin. Okay, so some of the most important points along these scales. Number one, absolute zero. Okay, on the Kelvin scale, this is 0 Kelvin. And by the way, I need to drop the degrees because we do not say degrees Kelvin. We say just the number Kelvin. But it is negative 273.15. On the Celsius scale, and it's negative 459.67 on the Fahrenheit scale. Okay. Freezing point of water. Now, we have to specify at standard temperature and pressure, or really at standard pressure. On the Kelvin scale, this is 273.15. This is 0 Celsius. And this is 32 degrees Fahrenheit. And then, of course, we have the freezing point, or the boiling point, rather. And on the Kelvin scale, the boiling point of water is 373.15. It is 100 Celsius, and it is 212 degrees Fahrenheit. Okay, so I'm not going to make you guys go through and derive the slope and intercept for all of the conversions from this, but do realize that these are linear relationships. Okay, so even though the scale degradations are not the same, in other words, a degree Celsius is not the same as a degree increment on the Fahrenheit scale, They are linear in that a given increment on the Fahrenheit scale corresponds to a given increment on the Celsius and Kelvin scales. Now, the increments of Kelvin are and Celsius are the same. Okay? So that means that a delta T in K and Celsius are same. But for Fahrenheit, that's not the same. Okay. And you only need to look at these two points right here, the freezing point and the boiling point, right? There's 100-degree difference or 100 scale increment scale difference between Kelvin for the freezing point and the boiling point. There's 100-degree increments between freezing and boiling for Celsius, but there's 180 there's 180 on the Fahrenheit scale. So that gives us the fact that a degree change on the Fahrenheit scale is less than a degree change in Celsius. Okay. But here are the only two relationships I'm going to give you, and you can rederive anything else you need from these two. Okay. So the Fahrenheit to Celsius. So if you need to go from Fahrenheit to Celsius, your temperature in Celsius is going to be given by 5/9 your temperature in Fahrenheit minus 32 degrees. Okay? And if you come back here, you can kind of see where this is coming from. We anchor our temperature scales in normal everyday use at the freezing point of water, and there's a difference of 32 there. So you're going to get a factor of 32 difference between the two scales for that particular point. And then the 5/9 comes from the fact that 100 over 180, so these are the increments on, for every 100 increments on the Celsius scale, you get 180 on the Fahrenheit scale. And 100 over 180 is 5/9. Okay, so that's where this equation, or at least these numbers, are coming from. These are not just pulled out of a hat. All right, and then your Celsius to Kelvin, whatever my Celsius temperature is, just add 273.15 and you'll get your temperature in Kelvin. Okay, so by extension, we can immediately get from Kelvin to Celsius. Okay, so room temperature what is room temperature, or 70 degrees, in Celsius and Kelvin? Okay, so to find the temperature in Celsius, we just take 5/9 times our temperature in Fahrenheit, 70, minus 32. Okay, so 70 minus 32, 38. And then we multiply that by 5/9. And when I do that, we get 21.1. So very often we will say that room temperature, a lot of your problems you'll see room temperature of Celsius being approximately 20 degrees Celsius. Okay. So what is 21.1 degrees Celsius in Kelvin? So my temperature in Kelvin is my temperature in Celsius plus 273.15. So 21.1 degrees Celsius plus 273.15. And if I add 273 to 21.1, 273.15, 294.3. So very often you'll hear room temperature for the Kelvin scale being approximately, well, let me write it this way. Your room temperature in the Kelvin scale is approximately 300 Kelvin. Okay. That is on the warm side because those 6 degrees between 300 and 294 do play a strong role. But that is basically the idea. Okay? Okay, so there we have an introduction to temperature and thermal equilibrium and temperature scales. And up next is thermal expansion and heat capacity.